بسم الله الرحمن الرحيم. اليوم محاضرتنا في numerical methods راح تكون عن the last chapter in the course related to numerical differentiation and integration. احنا عادة ممكن نصادف اللي هو numerical differentiation and integration ممكن يكون له ثلاث حالات. يوم when we perform يعني عندما نساوي numerical integration and differentiation when we perform numerical integration and differentiation ممكن يكون عندي 3 cases بالنسبة للفانكشن أو للداتا اللي بنعملها integration أو differentiation. أول حالة the first case is the function to be integrated or differentiated is a simple function like exponential, polynomial or trigonometric. The second case is a complicated continuous function. وهذا complicated continuous function بيكون صعب إن لم يكن impossible to differentiate or integrate. والحالة الثالثة يكون عندي مش functions بيكون عندي data discrete data points اللي هي مجموعة من data points xi f of xi from I equal 1 to n وبالتالي بدنا نعمل integration أو we want to perform integration or differentiation based on discrete data points. هسه الثلاث حالات. الحالة الأولى إذا كان عندي simple function ساعتها يفضل التعامل معها اللي هي باستخدام الكلوزد فورم أو الاناليتيكال ميثودز اللي مرت في معكم في كالكولاس 1 and 2. بس إذا كان عندي الحالة الثانية والثالثة اللي هي إذا كان عندي complicated function أو tabulated data معناته ما في مفر إلا إنه نستخدمها numerical integration or numerical differentiation. بنبلش في أول section من الشابتر اللي هو numerical differentiation. differentiation numerical differentiation بيعتمد على numerical differentiation formulas وهاي الفورمولاز عادة اشتقاقها بكون مبني على one of two main methods إما عن طريق التايلور سيريز expansion أو عن طريق interpolating polynomials زي اللي مروا معنا في الشابتر السابقة اللي هي لاجرانج ونيوتن وعادة بنستخدم اللاجرانج interpolating polynomial. هسه الفورمولاز differentiation formulas ممكن تصنيفها ل 3 categories بناء على الداتا بوينتس اللي احنا بنستخدمهن في الديفرنشيشن او في الديفرنشيشن وين موقعها للداتا بوينت اللي بعمل عندها انا الديفرنشيشن. بالتالي اول حالة اللي هي الفورورد ديفرنس فورمولاز، الحالة الثانية الباكورد، والحالة الثالثة اللي هي الهايبريد. اوكي في الفورورد assume that I have like this case. Okay, this is the point where I am standing I اللي هي عند xi here x I minus 1 here like I minus 2 here I plus 1 and here is I plus 2 and so on. In the forward differentiation formulas I am interested in finding the value of the derivative. I am interested in finding the value of the derivative, okay, at xi using all of the nodes and data points to the right hand side of my position like I plus 1, I plus 2 and so on as given in this equation. So I am evaluating the kth derivative at the ith node xi using all of the nodes that are to the right hand side of xi plus 1, xi plus 2 till xi plus r. And we call this formula r plus 1 forward formulas for the kth derivative. Okay, and generally we use it at the starting nodes. So this is the forward that we are standing at certain position and we use all of the nodes to the right hand side that are larger like in terms of x. The second one is this, it's the backward, it's the opposite. I am standing at xi and I am using all of the node to my left. The value of xi minus 1, xi minus 2, they are less than the current node. So we are calculating the value, the kth derivative at xi, and we are using xi minus 1, xi minus 1 till xi minus l, and we call it l plus 1 point backward formula for the kth derivative, and normally this is calculated for the final nodes when xi is at the final nodes. And the third category is the hybrid. Hybrid is a mixture between the forward and the backward. So we are standing at like this location, and we use some of the nodes to the right hand side and some of the nodes to the left. So hybrid, it's mixing between forward and backward. So here we are calculating the kth derivative at xi using some xi and some of the nodes to the right and some of the nodes to the left. And this is called L plus R plus 1 hybrid formula for the kth derivative. And normally we use it away from both ends, like when we are in the center. Okay, so this is what we mean by forward, backward, and central derivative. Okay, so there is one special case of the hybrid. Okay, a special case of the hybrid. It's called central formulas. Central formulas, if R and L, they are equal. So the number of nodes to our right hand side is equal to the number of nodes to the left hand side. So we call this the central formulas. Okay, and graphically, if we take it graphically, let us, here we have like three nodes, xi plus 1, here xi plus 1, and here xi minus 1. Okay, so in the first case we are calculating the black one is the true derivative, while the dashed one is the approximate derivative. So in this case, this figure, we are calculating the derivative at this node and at this node, so it's forward because from our location and to the right. While in the second case, this case, we want to find the value of the derivative here based on this node and this node. So we are taking the nodes to the left of our position, and this is, we call it backward. While in the third case, we are using some of the right, some of the left, and this is the dashed line is the derivative. So we call it the central. So here A is forward, B is backward, and C, figure C is so this is central, this is backward, and this is forward. Okay, now after the introduction of forward, backward, and central or hybrid, we will use Taylor series for the differentiation of the formulas to derive the values of differentiation based on Taylor series. So we have taken in chapter 1 Taylor series that assume that we want to find the value of a function at xi plus 1 or xi minus 1, say like this, in terms of the function values and its derivative at another node. So xi, f of xi, f prime, fn derivative of xi. So the Taylor series we have taken in chapter 1. F of xi plus 1 is equal to f of xi plus f prime multiplied by the difference between the two nodes. And f double prime divided by 2 factorial multiplied by the difference to the power 2, and so on. And this goes to infinity, if you remember. If we assume that the difference between xi plus 1 minus xi is equal to h, and we have uniform step size for all of the nodes, then f of xi, this equation is reduced like this: f of xi plus f prime h plus f double prime h squared, and so on. Okay, and if we want to find the value of f of xi minus 1, not plus 1, so we will have similar case, and this will be the formula. Okay, but the only difference is that we have here, it will be in this case xi minus 1 minus xi. So this will be not h, this will be minus h. And this is why here some of the terms, they are negative. Okay, so this is why, because we are calculating at the node xi minus 1 using xi. So the difference will be negative, minus h. Okay, and here Rn in this equation, the remainder term, and here is related to the first term in this term, in this Rn, is the n plus 1 derivative, okay, and its h power is n plus 1. So we express it in big O notation. We call this big O notation, and it gives you the order of the h, the power of the h value in the first truncated term. So OHn plus 1 means that the first truncated term, okay, the first truncated term has h power equal to n plus 1. The first truncation term has the power of h is equal to n plus 1. Okay, so we can proceed. Here the remainder term, as I mentioned, Rn, okay, it gives us information about the number of terms that are missing, that we dropped, that we chopped, okay, from the term n plus 1 to infinity, okay, because we know that Taylor series is an infinite series. So what does this OHn plus 1 means? Means that the truncation error is of the order h to the power n plus 1. Okay, and this means that the error is proportional to two factors. So here we have h to the power n plus 1. So the error is related to the step size from one aspect and to the number of terms n included in the approximation from the second side. So here h to the power n plus 1, it gives us that there are two factors that control the truncation error. Number one is h, okay, the value of h. The smaller the value of h, the smaller the truncation error. And number two is the power of h, which is n plus 1, which gives us the number of truncated terms. So as the number of included terms, which is equal to n, is increased, this means that it will be better approximation. Okay, so it's written here that the error is proportional to both the step size and to the power. Okay, so why we use this OH to the power n plus 1? To compare the numerical error using different formulas. So if we have two formulas, one with OH and another one with OH squared, okay, if we have two formulas for differentiation and one has a big O notation of OH and the other has a big O notation of OH squared. So assume that we have halved the step size. The step size is reduced to half of its previous value. That assume that we solve it using h, which has certain value, any value, and then we repeat it with h1, which is in u, which is h over 2. So we half the previous h. So what will be this effect of reduction of this step size on the error? In case of big O notation, h, it will be reduced in the same margin. So it will be reduced by 50%, half. While if h, the big O notation, is OH to the power 2, this means that the half will be to the power 2. This means that it will be 1/4. So the error will be reduced to quarter, to its quarter value of the original one. And this is, it's clearly written here. Okay, it's clearly written here that having the step size in OH, it will have the error, while if it is OH to the power 2, it will quarter the error. Okay, so how can we reduce the truncation error? By the addition of more terms in the Taylor series. So in Taylor series, lower order terms, they have more contribution and more share than higher order terms. And as a result, Taylor series, it becomes more accurate by reducing the step size h or increasing the number of terms, which is n. So this is obvious from OH to the power n plus 1, which might be reduced by decreasing H or increasing and the number of terms. Okay, so now we will go to the first to differentiate our first formulas. Okay, so now we will take the forward divided difference. So here we have fxi plus 1 is equal to f of xi plus f of xi f prime of xi h plus oh to the power 2. We are taking only the first order approximation, only taking into consideration till the first derivative. Okay, and here we are using, this is the forward, because we are using the nodes to our right hand side. So after manipulation, we will reach to this formula, f prime of xi is equal to f of xi plus 1 minus f of xi divided by h, and the big O notation, the truncation error is proportional to OH. This is for the forward divided difference first derivative. Now we will go to the backward. For backward, we will do the same thing, but we will extend the series at xi minus 1. So we will f of xi minus 1 will be f of xi minus this plus this, and we will take this first order approximation. So all of the terms from the second term, okay, and above, they will be truncated, and we will reach to this formula. So the big O notation, it has the power here h squared, which is the same as the order or the power of h in the first truncated term. So if we perform certain manipulation, we will get the first derivative for the backward case is equal to f of xi minus f of xi minus 1 divided by h plus big O notation h. So if we move to the central divided difference, and we take forward and backward series around xi plus 1 and xi minus 1, which are the two formulas that we have. Okay, and then we subtract this equation from this equation, okay, as given here. So we will get this formula. And if we manipulate and find this f prime, we want to find the value of f prime of xi, so that will be on the left side of the equation. So we will get f of xi plus 1 minus f of xi minus 1 divided by 2h, and the big O notation will be h to the power 2. So this is the formula, f prime f of xi plus 1 minus f of xi minus 1 divided by 2h, and the big O notation is oh squared as shown here. So if we compare the forward, the three formulas, this is the forward, and this is the backward, and this is the central. Okay, we pay attention to the big O notation. In the forward it was OH, in the backward it was OH, while in the central it was OH squared. What does this mean? This means that the central has OH squared truncation error, while forward and backward has OH, which means that central is more accurate than the forward and backward. Okay, now we will continue and see how to calculate higher order derivatives. Like, assume that I want to find second derivative, third derivative. So it's also based on Taylor series, but at Taylor series expansion for different nodes. So we will expand the Taylor series at xi plus 2 in terms of f of xi. So f of xi plus 2 in terms of f of xi, and here it will be the value of the difference will be not h, it will be 2h. Okay, and here we have the expansion of f of xi plus 1 in terms of f of xi. So if we pay attention to both equations, here it's f of xi 2h. Okay, and here if it is f prime of xi multiplied by h. So we are interested in finding the second order derivative, this term and this term, second derivative. So we should cancel the first derivative from the resulting equation after manipulation. So how can we cancel? If we perform this equation, if we say f of xi plus 2, which is this equation, minus 2 f of xi, minus 2 multiplied by this, then the first derivative will be cancelled. And we will get the second derivative as our first derivative. So we will get here f minus f of xi plus f double prime of xi h squared plus oh to the power 3. So after manipulation or rearrangement, we get this formula for the second derivative, which contains 3 nodes and divided by h squared, and here the big O notation, it's OH. So this is for the forward second derivative. Now we will perform similar thing for the backward second derivative, using in the same manner, in the same procedure, the expansion at xi minus 2, which is like this, and the expansion similarly at xi minus 1, which is like this. And we will do the same subtraction process, and we will get finally this one, and after arrangement we will get this second derivative. Okay, but this is backward. Like, pay attention to here that we are using nodes xi minus 1, xi minus 2, so all of the nodes are to the left, while in the previous one here in the forward we are using xi plus 1, xi plus 2, and xi, so all of them are to the right. So finally we will reach to the central second derivative. So we will have f of xi plus 1 and f of xi minus 1, the expansion, and we should add both equations in order to get rid of this first derivative. So after addition we will get to this, we will get, sorry, this after the addition we will get this equation, and after rearrangement we will get the second derivative, which is equal to this. And pay attention that here OH is to the power 2, while in the previous two cases it's OH to the power 1. So which means that the central derivative is more accurate than the backward and forward derivative formulas. So now we will take an example. We will take an example that we have a certain function, fourth order polynomial, and we want to find the forward, backward, and central approximations to find the first derivative with two different step sizes. One is at h.5 and one is at h.25, and we want to find the derivative at the node xi is equal to 0.5. So the first thing, in order to find the derivative, is to take one of the cases for h, which is equal to h is equal to 0.5, and after that to sample the base points and then to find their function values. So here xi is 0.5, xi minus h will be 0, xi will be 0.5, and xi plus h or plus 1 will be 1, and we find their values here from the polynomial. And after that we plug those values where in the derivative formulas, and we get this error 50, like 8%, 39%, and almost 10%. And now we will repeat it with h is equal to 0.25. So our reference node is 0.5, and xi plus 1 will be 0.75, xi minus 1 will be 0.25, and we will find their function values from the polynomial. And after that we find the forward, backward, and central first order derivative, and their values are given, the true relative error are given here. If we compare those true relative error with those, we can notice then that for the forward and backward, those errors almost 50%, half of the error of those two values, while for the central this error is not half, is almost 1/4 of the error for the central. And this agree with the theory that we mentioned, that in the forward and backward we have our big O notation OH, while in the central we have OH to the power 2. And what does this mean? If we reduce the step size to half, this means that the error in the forward and backward will be reduced 50%, while here it will be quartered, or it will be reduced to 25% approximately. Okay. Okay, here we have some few notes. The derivative represents the rate of change of certain dependent variable with respect to an independent variable, and the first derivative represents the slope of the tangent at point xi. And if we want to get more accurate formulas for certain derivative, whether first or second, so we can obtain it by substituting approximation for higher derivatives of Taylor series. And in this way, we increase the number of points for the derivative, and this will increase the approximation. So, for example, we have this formula for first derivative. It was like this, and this was the first truncated term, and then OH squared. So, if we have derived the value for the second derivative, and it was like this. So, if we substitute this formula here instead of this second derivative, okay, what we will get? We will get the value, and this is the formula. And in this case, the number of points for the derivative have increased from 2 here to 3. Here they are 3 data points, and they are all forward. And while moving from 3 to 2, the truncation error has been reduced. So again, there are two main ways to improve the derivatives. Number one is to decrease the step size, and number two is to include more terms. And inclusion of more terms means that more points are included, and this reduces the error. And all of the formulas that we have derived till now, they are based on the step size is h is uniform, is constant. So we call it constant or uniform step size. So what we have, if we want to calculate the derivatives for not uniform step size, non-equally spaced data, then we used interpolating polynomial like Lagrangian instead of Taylor series. And there's another note that as the derivative order increase, the number of points required to find that derivative increase, and there is a formula that the minimum number of points for any derivative equal the derivative order plus 1. So assume that we want to calculate the second derivative, there should be at least 3 data points. If we want to calculate the fifth derivative, there should be at least 6 data points. Okay, so this equation relates the number of points, the minimum number of points, with the order of derivative, and there is an increment of 1 between both of them. So here in those tables, I am listing for you a number of forward difference formulas for the first derivative, second derivative, third and fourth derivative based on different number of points. Like in the first case 2 and 3, and here 3, 4, 4, 5, 5, 6. And as I mentioned, like for example, the fourth derivative, what will be the minimum number of points to calculate it? It will be 5. So this is the minimum. We cannot calculate the fourth derivative with 4 data points or 3. And for example, here the second derivative, the number of points, the minimum is 3, and we can go up in 4 points and so on. And this is the forward. If we proceed, this is the backward. This is the backward difference formulas for the first, second, third, fourth, and using different number of points as I mentioned. And if we also proceed, this will be the last one, will be the central difference formulas, okay, for the first, second, third, and fourth derivatives. And we will have example. We will have example. This is a function, and we want to repeat the computation of example, the previous example, using the higher order formulas which we discussed just now. What this means? This means that we want to use 3 points formulas for the forward and backward, and we want to use 5-point formulas for the central. And we want to calculate the value of the first derivative at xi, okay, using step size of 0.5, and this is the sampling of the data, and here the value of the function. And we are finding here the value for 5 points, okay. And here we are plugging those values, okay. And if you pay attention, forward, backward, it has error, while the central, it gives you 0 error, which means that we got the exact value. And again, when we repeat with h 0.25 instead of 0.5. We have those points and we have the function values. And again, here the error is reduced in the case of forward and backward as compared to those values. Okay, while the true error is still for the central is 0. Okay, and in the last section of, in the last part of this section, I am listing 5-point formulas for the first derivative till the fourth derivative. Here is the first derivative, and here we are calculating the value of the derivative at xi, first derivative at xi. Okay, this formula is all forward because xi plus 1 plus 2 plus 3 plus 4, so this is forward. While if we take the last one is backward. Why? Because here it's xi minus 1 minus 2 minus 3 minus 4, all of the nodes to the left, while here to the right. And those three, they are hybrid, and the central one, the one in the middle, this one is the central derivative, so it's here central. Okay, because the number of nodes to the right is 2 and the number of nodes to the left is 2, and L is equal to R as I mentioned before. Okay, so if we pay attention to the truncation error in all of them, it's OH to the power 4. And also if we pay attention to the central one, Fi in this central one, Fi does not exist. So replace this F naught with Fi. So Fi does not exist, and this is why the truncation error in all of them was OH to the power 4. Okay, now we will take another one, which is the second derivative. Again, the truncation error for 5 points has been reduced from OH4 to the AH to the power 3 for forward and backward. Okay, while if we pay attention to the central second derivative, it has Fi here. Fi exists, not F naught exists. So since Fi exists, it has better accuracy, so its big O notation is H to the power 4, while other forward or backward, it's H to the power 3. Now we will switch to the third derivative. Okay, again, here Fi does not exist in the central. Here Fi does not exist, and in our case all of the derivatives, they are H to the power 2 approximation, big O notation. While in the fourth derivative, Fi exists here in the central, it's here, and due to its existence, okay, its accuracy OH is to the power 2, while all of the others is OH to the power 1. So what we conclude from this, that if the central node Fi is existing in the central one, then it will have a better approximation than the previous, the forward or the backward or the hybrid methods, formulas. While if Fi is missing, this means that it will have the same big O notation. Okay, so this is what we conclude from this, these formulas in the first thing. The other thing is related to the sum of the coefficients in each formula. If we sum up all of the coefficients in each formula, like all of those, their summation will be 0. So if you take this one, any one of those, the summation of all of the coefficients of any formula should be 0. Okay, so this is the second rule. The second rule is that the summation of all coefficients in any formula, they should be 0, because we are taking the difference and their summation should be 0. Okay, so this is the second point. The third point is related to the symmetry. What do you mean by symmetry? Okay, now let us take an example where F naught exists or Fi exists. If Fi exists in the central, okay, so there will be positive symmetry. What do you mean by positive symmetry? This means that this coefficient will be the same as this coefficient, minus 4 minus 4, and this coefficient will be the same as this coefficient, okay? And the coefficient of I minus 4 in this formula will be similar to the coefficient of this, and the coefficient of I plus 3 in this formula will be similar to this coefficient, okay? So there will be similarity between those and this and within this I minus 2 will have the same coefficient as I plus 2. I minus 1 will have the same coefficient as I plus 1. So the coefficients, they are the same sign. I plus 4 is coefficient like in this and this, okay? Like I plus 4 here, I minus 4 here is, they have the same coefficient, and so on. So this is the case where f naught or fi exist. While in the cases where fi does not exist, it will have a negative symmetry. What does mean this negative symmetry? That this node will have the negative of this. This will have the negative. This node will be the negative of this. This node 14 will be the negative of this. This 24 will be the negative of this. This 18 will be minus 18 here. This minus 5 will be 5. This one will be minus 1. This minus 6 will be here 6. This minus 12 here will be 12. This 10 will be here minus 10, and so on. And within the central, here minus 2, here will be 2. Here will be minus 1, here will be 1. So negative symmetry. And this is applied for all of the formulas, okay? And let us, okay, all of the comments that I mentioned, they are mentioned in this notes table, okay? So for odd derivatives that we discuss, f naught appear, while for even f naught does not appear, okay? And as the derivative order increase for certain number of points, like the fixed points, 5 points, the truncation error, the big O notation, instead of OH to the power 4 we start, then OH to the power 3, then OH to the power 2, then OH to the power 1. So the truncation error decrease. How to increase accuracy? Then higher order derivatives, okay? For higher order derivatives, we should increase the number of data points. And the power of h in all of the formulas that we discussed before, it's equal to the derivative order. What do we mean? Here, like here, OH to the power, in all of the differentiation formulas, here h to the power 4, and here is the fourth derivative. Here h to the power 3, and here is the third derivative. Here h to the power 2, and here is the second derivative, and so on. So the power of h in the denominator is equal to the order of the derivative. This is what do we mean by the mentioned point. And the summation of all coefficients in each derivative is equal to 0. Okay? And the coefficients are symmetrical around the central, okay, where f naught or fi exists, while the coefficients are symmetrical with opposite negative symmetry for the cases where fi does not exist. And as the number of points increases for certain derivative, accuracy increases. And as the order of the derivative increases for certain number of points, the accuracy decreases. Okay? And let us take few examples. Here we have second order derivative, and we want to find the first derivative, forward, backward, and central at xi is equal to 0.5 using h is equal to 0.2. And here we have sampled the data, we have find the function values, and here we applied for them. And here the epsilon t is equal to 0. That means that we have find the exact value. And in order to continue, okay, here we have a fourth order polynomial, and we want to find the first derivative using forward, backward, and central at this node xi using h, which is equal to 0.2, while the true value is given to us. So for h is equal to point 2 we sample the data, we find their values, and here we apply. Okay, and these are the graphs for the derivative. And again, the same function, and we want to use forward, backward, central for the first derivative with different step sizes. Okay, and for the first step size, these are the nodes and their calculations, and these are the derivatives, and these are the graphs. For the second step size, which is 0.5 of the previous one, this is the sampling process, and these are the values of the derivatives. And here the graphs for the derivatives. Okay, and in this example we have fifth order polynomial, and we want to use formulas for 3 points and 5 points to find the first derivative. 3 points and 5 points with two different step sizes, and this is the true error. So here we have 3 points and h is equal to 0.4, and we find the values. And again, for h is equal to 0.5, 3 points. And now we switch to 5 points, h is equal to 0.4, and finally h is equal to 0.2 and 5 points. And these are the formulas here or in the previous cases, and the following table summarize the results. These are the number of points, 3 and 5, with two different step sizes, 0.2 and 0.4. And we are using forward, backward, central for each case. Forward, backward, central. And here is the result, and here is the true error. And as you see, as the number of points increases, the error has been reduced. Okay, the error has been reduced. And in general, the central is more accurate. The central is more accurate than the forward and the backward in general. Okay, the central is generally more accurate than the backward and the forward. And by this coverage, we have completed the numerical differentiation section. And in the next lecture, we will cover the numerical integration section. Thank you, and wish that you understand this lecture. Thank you.